start on, so today we're going to start on free electron lasers, and in particular very short free electron lasers, X-ray and EUV. And it wasn't so many years ago that people thought that this would be such a challenge. It might never make it at such short wavelengths. When the first FEL was flash in Hamburg, ran in the EUV, people whirled around, were shocked. A little bit later, SLAC, Stanford, ran an X-ray, hard X-ray FEL, and believe me, the world was not prepared for it. Everyone was just in total shock. So we're going to go over today a little bit of what that's about. So this is showing a gain curve. So it's radiated power versus distance along the undulator. The scale here doesn't make so much sense for us. This is from a different application, but the diagram really captures what we're looking for. And that is in a short undulator. Oh yeah, so this is really a long undulator. In fact, the undulators that you'll see at the hard X-ray facilities, so at Stanford, in Japan at Sakla, in Korea at the PAL FEL, and in Switzerland, the Swiss FEL, and the other big one is the European, the largest of all, European XFEL, which runs between two German states. And for those, the distance, at least for the hard X-ray facilities, is almost a kilometer. In fact, it may be more than a kilometer in total distance. And so what happens here is in the first, as the electrons are moving through the undulator at the beginning, the behavior is a lot like the synchrotron radiation in that for the first few meters, you don't get any modulation and you don't get any enhancement. And the emission angle, which was critical in the first measurements that there was X-ray free electron lasing, one of the things that happens is initially you're looking at undulator radiation, and the half angle of the radiation cone, as you remember, is 1 over gamma squared root of n. And it's so many microradians, maybe 20 microradians or 15 microradians for hard X-ray. And then as you get moving, let's say with the SLAC X-ray FEL, where they're going out to a kilometer, they watch, first of all, they see an exponential increase in power. That's certainly a strong hint that something was happening, that was lasing. But they also saw, they were monitoring the radiation cone. And it went from a relatively large 15 microradians or something like that in the early parts. And then as they put more and more magnet sections into the electron beam path, that angle narrowed down. And it narrowed down because the radiation had become coherent. And because it was coherent, it satisfied that condition that we've talked about so often, d dot theta, full width at half max, roughly equal to lambda over 2. And what happened was coherence had taken over, and the angle also collapsed. So it went from something like more than 10 microradians to around 1 microradian. And so what happens here is, as the undulator gets longer and longer, the initially random motion of the electrons, which the accelerated people and the free electron laser people, they wouldn't call it undulator radiation. They call it spontaneous emission. And it's just going over large angles. Anyway, that starts, and then at a certain point, the radiated electric field starts having its effect on the randomness of those electrons within the beam. And they start to form into a little, an electron wave. So it starts way back here, and once it starts, you'll see why, there's an exponential growth, and this modulation becomes deeper. The modulation depth becomes deeper, and measured in electrons per cubic centimeter, let's say, and also how many electrons are participating in that. And eventually, you get to a point where there's essentially a fully ordered electron beam, okay? And this process, by the way, is called SASE, self-amplified spontaneous emission. meaning it starts with spontaneous emission and it self-amplifies. So, okay, sassy. Okay, what we're going to find in the next, I think sometime today, maybe into tomorrow, next class, that there is a gain length that depends on the undulator period, some constants, and what is called the FEL parameter. We use the Greek letter rho, and it's a non-dimensional number. So gain length is the undulator period, which could be something like 3 centimeters, divided by the FEL parameter, which would be a little bit less than 1 part in 1,000. So it'd be like the gain length would be something like 1,000 undulator periods. Okay, and this undulator, this FEL parameter, which is shown here, it's a complicated thing. It drops out of the math. You have to put some effort into the math to get this, but basically it just drops out. You'll see more about that today. And it's an important parameter. It gives you the gain length. It gives you the saturated power that you're going to get. The saturated power, we'll see, is the same non-dimensional parameter multiplied by the energy, the total energy in the electron beam. This is the energy of a single electron, and the current I divided by E is the total number of electrons. Okay, so this is the saturated power, and the relative spectral bandwidth also depends on this FEL parameter. Okay. Okay. And our condition of d dot theta in RMS quantities, we would have had d dot theta equals lambda over 2 pi. So that's right, yeah, lambda over 2 pi. They would use sigma values. So their half angle is RMS quantity is sigma prime. Their beam width RMS quantity is sigma. So we would have put a 2 here, and that would have made this lambda over 2 pi when we wrote this in terms of RMS quantities. But they don't do that, and I just thought I'd tell you now, in case you look someplace else, they always write sigma sigma prime equals lambda over 4 pi. That's what they recognize. If they see me writing it with a 2 pi, I have to explain it to them. Okay. Okay. So these are desirable quantities of an X-ray laser. So first of all, photon energies, either hard or soft or in the EUV. High photon flux, meaning how many photons per pulse or peak power. Short pulses, a few femtoseconds to perhaps 100 femtoseconds. So most normal operating is less than 100 femtoseconds. And for instance, the Japanese facility called SACLA, S-A-C-L-A, typically runs at 10 femtoseconds. So the people in Michael Zertz's group who will go there will typically see a 10 femtosecond pulse. There is true phase control. It's really spatially coherent. The power really goes there is really an n squared effect. The n here will be the number of electrons in the bunch, which is usually around 10 to the 8th or maybe even 10 to the 9th, depends on the photon energy. They generally have a broad tunability in energy. And by the way, you know, we saw undulator radiation, for instance, at the ALS or APS, that was tuned by the magnet period, choosing your magnet period and then opening and closing the magnet structure. But with the FELs, there's a little variation here. Sometimes they just change gamma because they don't have 20 or 30 end stations. They just have one end station or maybe 2, and they only do one experiment at a time. So they can just change gamma. In some cases, they'll also change the undulator period because they want to have one soft X-ray station and one hard X-ray station. And polarization control, with FELs, it's certainly an interesting property of the radiation, and you can change it. And you'll see that this kilometer length of undulators is made up of maybe, I don't know, divide by 5 meters, something like that. It's made up of a bunch of sections, magnet sections with the exact same period, and they insert all of these things into the beam path. But maybe I should wait till later to say this, but I'm into it. In the kilometer of path length that you might have in one of the facilities, the first 800 meters or 900 meters is sent just in going from chaos to a high modulated electron beam. Once you have the high modulated electron beam, you can send it through the last few magnet structures with different polarizations, and they will radiate. And those last sections become known as the radiator section. It's where most of your power comes from in any event, but you can actually change the polarization. So you could have had some linear polarization all the way through for the first 800 meters, and then the next few sections you could have cross polarizers or an orthogonal polarization. So there's a lot of freedom here to choose that. Repetition is important. So for instance, until recently, slack has been, I think, at 20 hertz, and the new European facility is at a really high rate. So we'll look at those together. And synchronization. Can you do pump probe experiments, two color? Can you synchronize with a laser, which might have an even shorter pulse? Okay, so those would be important things. Anyone want to comment?
Why would we want to do different polarizations in the final sets of the?
Well, because you might want the outcoming radiation not so much to change from vertical to horizontal, but you might want to have elliptical or circular polarization. So you might use one of those Apple undulators we saw at the end of the last lecture that combine magnetic fields in the vertical direction and in the horizontal direction. So there'll be two undulators flipped, and you can make, in that way you could get circular polarization. So that would be I think the main interest, and that would be very interesting for looking at magnetic systems or any systems with spin, or for instance helical structures like DNA or something like that. If you scatter, if your polarization is rotating the right way with the chirality of the structure you're looking at, you'd get one scattering amount, and if you went the other way, it'd be different. So that would be some examples.
Cool.
So this is just a reminder. Oh, it's a reminder for a good reason, though, I think. So how does an undulator work? You know, we go through the periodic magnet structure, and we found it reasonable to split this calculation of what wavelength are we going to see on axis into two parts, right? The Lorentz contraction, if we're moving with the electrons see a periodicity reduced by gamma. So that's a Lorentz contraction like the meter stick. So that gives us the radiation in the frame moving with the electron, but then the observer or our experiment is in the lab, and this thing is coming at it, this bunch of electrons is coming at it, and they're radiating at this wavelength, but we see them our sample sees them with a Doppler shortening, and that gave us this almost the undulator equation, okay? Where the wavelength on axis is the undulated period divided by 2 gamma squared, a factor could be 10 to the 7th or more, and an off-axis component. And the FEL is, in a moment, you're going to see they drop this, because when you get to full spatial coherence and such small angles, microradians or half microradians, they just drop this term. They don't see off-axis, okay? But anyway, we have it. And then we said, okay, well, let's just assume that the gamma for both of these effects was the same as the gamma of the electrons entering, but in fact that wasn't really true, as they may enter with a Lorentz factor gamma, but once they're in it, the axial component of gamma, which is affecting both of these effects, is magnetic field dependent, and we got this undulator equation. So that's how we got the undulator equation. Now you're going to, and there are some people in the FEL community who would probably do that too. But yeah, I'm just going to jump ahead because it's where I'm at. in the FEL community, I'll tell you about this, but I don't think it's the most obvious way to understand it. They have what they call the slip condition, and that is that the electrons are actually not going at the speed of light. They're going close, but not quite as fast. And there's a difference in velocity between the radiation and the wavelengths. So there's some difference there. And we calculated that, so we know what that is. And there's some transit time to go through one undulated period. And they take this and they say that because of the velocity difference between the electrons and the photons, that in the transit of one undulated period, there will be one shift, X-ray wavelength shift. So this difference in velocity will lead to one wavelength shift every magnetic period. So remember, the magnetic period is going to be centimeters, but the wavelength is going to be angstroms or nanometers. So, okay, so how do they do this slip condition? They say that the difference in velocity is the speed of light for the photons minus the average velocity of the electrons in going through one cycle, and the transit time to go through an undulated period is lambda u over c, and the c's you can see cancel out, and vz over c, we calculated that before. This is what we got. This is where we did the effective gamma. But at any rate, they then take this vz over c, which we have solved, and put it into this equation, and they get this, that the undulator, the period on axis for an FEL is the undulated period over 2 gamma squared. Looks just like our undulator equation, and it is our undulator equation. It's just a completely different way of doing it. I suspect this was due to John Mady, who invented the FEL, because sometimes his manner of thinking was different. I guess that's how you come up with really great ideas. You think out of the box. He had a different way of looking at it. This is what he came up with. So that's the slip condition. I just thought you should know about it in case you're somehow or other involved at some point and someone's talking about the slip condition, you know what they're talking about. This is a diagram of the slip condition. The heavy black line is an electron, or if you wish, the whole electron bunch, but let's say a single electron going through one undulated period. So the electron is coming through and going like this and completing a full cycle, crossing the axis here and here at the ends of one undulated. Okay, and if there is an FEL wave, okay, electric field, X-rays with a wavelength lambda and electric field, and it's propagating also. So the X-rays are shown, they're going through one cycle in the undulated period, and the electron is sort of aligned with it, maximum electric field, aligned with the negative at the halfway, and then maximum again. So the electron slips one wavelength. It went from this peak in the pulse, and it slips back to this one. So it starts here, but it's here at the end. So that's the slip condition. So does anyone want to comment on that?
I mean, so I understand the math we just did. Given that this is true, I don't understand why the electron slips precisely one wavelength per period.
Yeah, when I said I didn't follow the logic myself, really. So let's see if we can work with that. They're saying that there is a transit condition. If in transiting the undulator, one period of the undulator, in that transit time, which is roughly lambda u over c, there is a difference of velocities of the electrons and the wave, the X-rays, and so they say that this is going to slip one wavelength. We know that the X-rays are going faster than the electrons. The electrons are going slower. And so there has to be a slip. There has to be some shift. And they're saying that, okay, physically their logic is that the shift which there has to be, the minimum shift is one wavelength for one period. So that's 1 nanometer over a period of a few centimeters. So that's as much as I can give you on the logic of this. Their slip is, this is where they start. Their physical understanding is there has to be a shift. It has to be whole numbers of wavelengths because we have a lot of interference phenomena here. And this is what they say it is. Okay, so I'm pretty sure that probably started with Meade. Okay, so here's our, yeah, go ahead.
Yeah, I guess similar confusion. So you, and what you said makes sense, that the electrons would be traveling slower than the radiation. And so so what we're basically saying is initially the electron and the X-ray are oscillating at the same speed, but then we basically know the electron basically can't keep up with the X-ray, and that sort of is what's creating our slip condition, essentially.
Yeah, well, for sure, we know, from our simple diagram, if you remember a long time ago, where we have these wavefronts all piling up, they're getting very, very close because the electron's going so fast, but the electron's not going at the speed of light. Right. And yeah.
Okay, thank you.
Okay. So here, this is again, the SASE process, self-amplified spontaneous emission. Okay, here's our undulated situation with a magnet structure which maybe is a few meters long, 3 or 4 meters long, maybe 5 meters long at one of the synchrotrons. The equation of motion to explain the behavior it involves the Lorentz force, but there's no applied electric field. The magnetic field is very strong. And the V is as strong as you can get. It's C. It's very close to C. So when we did the SASE, when we did the undulator radiation, we left out the electric field. We said there's no applied electric field, and the electric field generated by as a part of the X-rays, which has an electric and magnetic field, is extremely weak in comparison. So for the undulator at a synchrotron, this was our equation of motion. This is our equivalent of our F equals ma. With the free electron laser, this thing is, it's got these 3 conditions here at the bottom. It's a much longer undulator. For the hard X-ray machines, it's of order a kilometer. For the EUV, not so long, a couple of 100 meters maybe. There's a high peak current here. Here there's like, the current is kiloamps, whereas here it's like a half amp, 400 milliamps, 500 milliamps. And the reason for that is they want to pack a lot more electrons into that bunch, all radiating, so that they can form a stronger electric field. So in the Lorentz term, in the Lorentz force now, the electric field is not going to be negligible anymore because there's going to be so many electrons, about the same number, an increased number of electrons in the bunch because it has a higher peak current. All the electrons are going at the speed of light. So the difference, higher peak current, means more electrons in the bunch, okay? And also the electron beam, the transverse cross-section of the electron beam is much smaller. It's not elliptical. The ellipse came because the synchrotron facilities were sort of, they were not linear. They go around in a circle. And the electrons, because all of the radiation is in the horizontal plane, all of those radiated photons are giving a tiny little kick to the electrons and spreading out the beam into that ellipse that we saw, okay? In the free electron laser, that's not the case. So they can start with an electron beam of 10 microns in diameter, and it'll stay that way to the end. So they've got a longer undulator, which means a sort of n-squared effect. They have a higher peak current, again an n-squared effect, this time from the number of electrons in the bunch. And they have coherence to start with, so there's going to be some interference effects. Okay, so what happens is, starting with this injected beam, which I made it look a little bit smaller than this one. It was about as much as I could do and still maintain this picture of this electron wave which is developed. So beginning at the very beginning of the FEL, it's just random electrons, and behavior for the first few meters pretty much the same, except that it's a higher peak current, etc. Okay, and that leads to a very strong electric and magnetic fields in the radiated X-rays, and it's the electric field which now starts to come in and play a role. And that electric field provides a feedback mechanism, which we'll make an effort at explaining in a moment. But basically, it takes all this random motion and starts to impose, it actually starts early on in a few meters, it starts to impose a little bit of a wave-like nature to the electron beam. So and then as that goes on, that electric field now increases very rapidly, because the intensity, or the electric field, is now increasing very rapidly because there's a coherent effect. There's a coherent addition among the 10 to the 8th, or however many electrons are participating in this wave, okay? And by the end of the undulator, you're basically getting 100% modulation, okay? So this looks like it has the appearance of a transverse wave of electrons, okay? We're plotting electron density here, going up and down, going right down to the bottom, okay? And so this is the electron wave. This is the radiated, I'm sorry. This is a side cut of the electrons. So there's an electron wave here that's propagating along. And so the electron density is showing real peaks and real valleys. So what might start initially as initially spread out electrons here, of course there are going to be a gazillion of them within one wavelength, or at any rate very many. It may start out this way, but not, not too far into the undulator, a micro bunching starts to appear on the wavelength scale. So some of these electrons get spread out, and some get pushed back, some get pushed forward, and you start to see, if you were to plot electron density, it would be high here, somewhat lower here, and high again. And towards the end of the long undulator, there'd be very few, almost no electrons in the middle. It'd all be pushed together. So again, that's the so-called SASE process. It is possible to talk about seeding a laser so you don't start from noise, and we'll come to that later, unless someone has a question about it now.
Is the initial electron bunching just like a statistical process that occurs, or is there some sort of driving force behind that?
No, you're absolutely right, and it's a great thing to bring up just right now. So let me just see what the next, I'm going to answer your question, but I just want to see, yeah, this is a good enough place to talk about it. So initially, in this random bunch of electrons, 100 million electrons or so, it's just statistically likely to happen that there'll be some little bunches that start to appear where there are a group of electrons together. Again, 100 electrons out of 10 to the 8th doesn't seem like very much. So statistically, that's going to be a pretty frequent thing early on. And those electrons are going to radiate in phase. So those 100 electrons are going to have the radiation equivalent of not 100, but 10,000 electrons. So just a factor, just having a bunching of 100 of them will generate some small, some modest but noticeable difference in the electric force that's available. And if you can imagine, well, statistically, how about getting 1,000 of them? Then you get 10 to the 6th. You're getting into real effects. And so what's happening here is just out of the noise, this is the SASE process, out of the noise, there's just randomly going to be a point where some of the electrons start to form into a little wave, okay? And they produce, when they do, they produce radiation, which is noticeably stronger by n squared for the number of electrons that statistically happen to come together in just the right way. And so And that could happen in the, it could happen at 10 meters, it could happen at 30 meters. That's just statistically varying. So for instance, if you're at one of the SASE FELs, which would include Stanford and Japan and the European facility, the intensities vary pretty significantly early on. Eventually they get to saturation, and that sort of smooths out the intensity of the pulse at the end, but it doesn't completely smooth it out. So there's a statistical variation of the output intensity, just because you didn't know, because where this initial statistical clump appears could vary, okay? And then there's the exponential process. So thanks, that was a great question. Really fit in perfect. Okay, the bunching advantage in general. Should I just, yeah, this is a, okay. Right. Oh, I see. I'm catching up. So the first part is just about an undulator. And in the undulator, the power radiated is just proportional to the total number of electrons. So the 10 to the 8th electrons or something like that. Because you add intensities, you don't add electric fields, then square them to get the power or the intensity, right? So all of this, the first few lines, is about an undulator at a synchrotron facility, okay? And the power is proportional to N. In the FEL, lasing starts early on, and it leads to bunching of the electrons, which I call capital N sub E, meaning total number of electrons. So we said in one of these pulses, I said there's like 10 to the 8th or 10 to the 9th electrons in the bunch, the big bunch that's going to come through here. The reason I put the letter J is, it become clear in a moment, that statistical bunching, I'm going to go backwards. That statistical bunching, I said, it could have happened anywhere in the bunch here. So there could have been some little fluctuation of electron density here, and that would lead to lasing. But it equally could have happened, let's say, in the back or the middle of the bunch. And it turns out the bunch is long enough that it'll support several of these little micro bunchings. So you can wind up with the electron beam coming out and not looking, as I've shown it here, ideally, with all of the electrons participating in one wave, but in fact can happen that there's a bunch of these micro bunches within the macro bunch. Am I going backwards? Yes, I am. Oops.
Wait, so Professor?
Yeah.
What you just said means there could be, because like there are already micro bunches kind of in the previous slide, but they could be like separate from each other.
Yeah, I got a little ahead of myself. Let me look ahead a slide or two and see if the slide which explains that is here. We're going through everything and we're not getting there. Okay, I'll just have to tell you about it. Yeah, so within that electron bunch of maybe 10 to the 9th and having the bunch length of a few centimeters, okay? Within those few centimeters, there could be a couple of those, there could be actually many of those little electron waves, if you will, that I was showing you. So rather than just one taking up the entire path, it turns out that there'll likely be quite a few. And in fact, this was some numbers. I made this slide because of a great interaction I had with the FEL community one year. They invited me to give an end of the day talk on coherence and how it plays a role in FELs. They were more into the accelerator physics of it. And what we came to understand together was that there wasn't a single what I would call a micro bunch, but there's a whole bunch of them, J, okay? And you'll see it's like 100. For SLAC, it's of order 100 of these things, and they can all have slightly different frequencies, okay? And that's statistical also. So as you're going through this amplification process, pulse after pulse is coming, the little statistical clumping that could happen in a few different places will lead to some amplitude, intensity fluctuations, but they could also have slightly different wavelengths within the bandwidth of the undulator. And we'll see it later. For the SASE process, it's a significant pain in the neck, and they have found solutions to it by what they call self-seeding, and we're going to get there, probably not today, but maybe tomorrow. Okay. So this is just a summary of the process, okay? Uniformly distributed particles enter the undulator. There's initially an emission of radiation, which the accelerator or FEL people would call spontaneous emission, what we called undulator radiation until now. The wave grows, the X-ray wave grows in amplitude and begins to affect the particle dynamics because the electric field is getting stronger and it starts affecting the acceleration. What we'll see in a moment is that a key thing is that there's a transverse coupling between the radiated field and the velocity of the electrons in the undulator. So the radiated field becomes strong enough that the velocity of the electrons is not only affected strongly by the magnetic field, but the radiated field starts to come in there. And so you've got two effects going on at the same time, okay? This is the equation for the rate of change of energy. You know, if we left out this middle part with d gamma dt, the rate of change of energy is F dot V. So we all know that from basic class in physics, okay? Relativistically, this is the way it turns out. This is the way it looks, okay? And the F dot V is the transverse electric field with the X component of velocity. They're lined up. There's a dot product there. There's an energy transfer. So the rate of change of the electron energy is shown here. So there is a change. Some electrons are going to slow down and some are going to speed up, and it depends on this dot product. Is this, these things are sinusoidal. And so is this resulting in a negative or a positive? It could go either way. So there's an energy exchange. Initially, it's zero. You lose as much going one way as you lose the other way, but after a while, there's a modulation in these velocities leads to a bunching on axis, and I have a diagram which I hope we'll see. That one of the key things here is that radiation power depends on the charge squared and the acceleration squared, but the charge squared is the number of electrons in the bunch squared. So we'll see that we can get a radiated power is going to go as the electric field squared, and that's going to depend on the number of electrons squared, and there's a lot of electrons in that bunch, so it can really make a big difference, okay? So stronger fields drive stronger transverse velocity. Stronger transverse velocity of the electrons drives stronger bunching. They radiate even stronger electric fields, dot, 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 dot. That's the feedback message. That's the loop for the feedback for the lasing action. So I thought I'd give you two examples of things that are unusual. You know, usually you think if you have an ordered system, thinking about the entropy of a system, the orderliness tends to go down, right? You start with something orderly, you get to chaos. You don't normally start from chaos and get orderliness. You have to do something. You have to put energy into the system, and you need a mechanism to do it. So I have two examples here, and I'm sorry, I forget if I showed you this already, but basically this is a football game, a soccer game, and that's some big stadium, and people come in and they randomly clap, and that's the chaotic start. for their team. But some group of people, and if you've been to a game, it definitely happens, they come in and they may be 10 or 20 of them together with their colors, and they start clapping together, and they clap together. They are sitting together and clapping together, and their pressure waves are going as n squared, where n is the number of people. And so for people, their pressure waves that they're launching by clapping are felt by the people near them, and it dominates. And people near them who were randomly clapping before now start adding to this group, initial group that started this. And it's a wave that spreads, and it spreads quickly, exponentially, because the number of people clapping coherently is going up rapidly, and that can spread through an entire stadium, and as you may have heard, leads to breaking of windows in nearby apartment houses and the like. So it can be a deafening effect. A similar thing happens at concerts, musical concerts. For instance, in Europe, this is a paper that was published in Nature about people at the end of a concert. They start randomly clapping, but they intentionally want to clap together to make it louder. And so they call it synchronized clapping. And I've never heard it myself, but I'm told it's not unusual in Europe. This is a simulation. This is from Sven Reike. It was his PhD thesis when he was a student in Hamburg, and now he's at the Swissfeld. And this has to do with the parameters of what was called Tesla. It wasn't an FEL, but it was headed that way, and Tesla became Flash, and Flash was the first short wavelength FEL. In fact, so it radiated, it says here, 109 nanometers. And at the time, it was shocking. It was such a change in wavelengths, okay? And these are some of the parameters. So this is a bunch of random electrons. They're going through a magnet structure. And so this is distance through a magnet structure. And and they're sort of, the spatial scale, I think, is wavelengths we're going to see in a moment. And as they go through, their randomness starts to, there's some statistical development, these little clutches of electrons that start forming a tiny wave, okay? And this is a simulation from Sven. So you can see at a certain point, he's got a high electron density here, high electron density here, high here, not so many electrons in the middle. This is looking like what I would call an electron wave, which is moving through the undulator, okay? And these electrons, which would normally have radiated electric fields, which were incoherently related to each other, because of the random motion, now the electric fields here, all of these electrons are radiating roughly in phase and are going to add, not only that, they're going to add with this group also, because they're just separated perfectly by one wavelength, etc. So all of the electrons here and here and here, etc., are going to radiate in phase. The electric fields will radiate in phase. Okay, this is just in case the movie didn't work, we'd have what you see, okay? Oh, did someone want to ask a question or comment on that? Did it make it clearer now why I was talking about this as electron wave?
So one thing that I noticed in the diagram is that your electrons are slightly bunched behind like the integer values. Is that related to the slip condition, or it's like they're not quite set on the integer values from the images? It looks like they're slightly behind.
Oh, here. I don't think it matters. I think this is just a scale. What matters is that they're a wavelength apart. How they match to the scale he chose. Maybe there's some significance, but if there is, I don't know of it. Yeah. Okay. Thanks. Okay, so this is an important slide. This is one that really gets to the physics of it. The math will come later, but what's happening here is there is some wave started, you know, going along with the comments earlier. There was some statistical fluctuation and a few thousand electrons got together in just the right way that they started producing a decent amount of coherent addition of electric fields. And now here's some little wave coming. It's a small amplitude. It's just starting the process. And this is this purple that's shown here is the electric field amplitude varying at some wavelength, lambda sub x, okay? And the electric field is pointing up. And there's electrons. This is the wave, and the black line is again the 0th order electron motion through one period of the magnet structure, okay? But there's a lot of electrons here, and so this black line is for one group of electrons, which is very slow, which is well matched here, but there's electrons all around here. This thing is just a few wavelengths long, but the bunch, the electron bunch, is much longer. So there are electrons here which are going to follow these paths. There are electrons here which are a half cycle behind, okay, and they're out of they're matched with a different phase, the opposite phase. So what's happening here? The trajectory of the electrons is shown in a solid line, and it would come if there was no electric field or a weak electric field. This electron or bunch of electrons in this close proximity here, they would follow the black line. They would follow the heavy black line, and they would cross the axis here. But because there is this wave, X-ray wave or EUV wave, the electrons right here feel a kick rather. They feel a kick, and their velocity changes, and they go up a little higher. And as a result, it takes them a little longer to get back to the axis, okay? So they had a certain momentum in this direction, in the z direction, but the kick-off axis has caused them to come back. So electrons that used to be here are now over here. So that means there's less electrons in this region than there was, and there's more over here. And likewise, for electrons which were a little bit behind this group that were over here, they got to kick the opposite way on a wavelength scale, so half wavelength here. And as a result, they didn't go as far before. Their kick was the other way, so they came back to the axis a little bit earlier, okay? And so this is leading to a bunching. This is how the bunching starts. Some electrons which would have been here are pushed forward. Some electrons which would have been just behind that are pushed back. And this causes the bunching on a wavelength scale, okay? So that's the main story here. And this energy equation, again, is shown here in, for relativistic things where the mass is a constant and the rest mass is a constant, and gamma is mc squared, okay? So this is one of the more important figures in physically understanding how this wave is producing this micro bunching. And then you can see as the wave, and these are moving together, by the way, this wave and this and the X-rays and the electrons are largely moving together. It's true they shift one period in this, but they are basically moving together. So this is a long time here for this process to take place. This is just to show you the scale of things, because the last diagram was not quite the scale for me to be able to get it all in one drawing. So here's an undulated period. Here's an electron trajectory. And it's just some things to show you that the wavelength, what we were looking at before, would have been very short. This was centimeters. This wavelength here was angstroms or nanometers. Remember, Lorena, you were asking about, or we were reaching the point of asking, how many of these electron bunches, how many of these waves of electrons are there in a wave train? And so I have some numbers from LCLS, the Linear Coherent Light Source at Stanford. This is some of their parameters in the old system. And they have the length of the beam. This is a full width at half max. So 2.35 times the RMS length in the axial direction of the electron bunch is 21 microns. So this is a full width at half max number. Okay. And by the way, you'll see this 2.35 over and over again. It's the conversion from RMS to full width at half max. If you have a Gaussian with a sigma z, with a sigma value, 2.35 times sigma is a full width at half max. So you see this over and over again. Okay, so it's 21 microns. And it turns out that those little waves of electrons only have maybe 300 periods. So the electron wave I was talking about isn't as long as the whole electron bunch. It's only got several hundred. I say 300 here, although in the example I gave 500. Did I get that right? But at any rate, this is how many bunches you could see. It's an estimate. So you'll see hundreds of these little radiating micro bunches, different intensities, perhaps slightly different wavelengths, all within the bunch length.
Professor?
Yeah.
I guess I don't really understand beyond like statistics happen why they should be slightly different wavelengths, the different micro bunches.
Well, for one thing, no, that's a really good question. There is a bandwidth associated with an FEL pulse. Let me just leave it at that for the moment. And that bandwidth depends on the rho FEL, that FEL parameter, which was something like 1 part in 400 or 1 part in 500. And so that sets a bandwidth to the whole thing, okay? And that means that if 1 part in 500, that means that that wave train, that electron wave train, probably only has about 300 or 500 cycles to it. It's associated with its bandwidth. If its bandwidth was narrower, it could be longer. But the Sassy process doesn't support that. The Sassy process only supports a bandwidth of something like 1 in several hundred.
Okay.
Does that?
Yeah.
Almost.
And then obviously, like if their wavelengths aren't perfectly the same, they can't be perfectly in phase, but will they be generally, the different micro bunches generally in phase with each other?
No, actually, great observation. So you got all these little bunches. In fact, I'm going to go look for the slide now, which means I'm going to have to get out of slideshow and go back to the slide sorter. But no, all of those little bunches, within their own little bunch, their many electrons are radiating in phase. But there's another little bunch, a little bit, a couple of hundred microns away, and they're radiating collectively themselves. But the phase or even the frequency, wavelengths, could be slightly different. So in general, they're not. They're each growing exponentially by themselves, and they're not phase related to each other.
So then how does that affect our like coherence properties?
Each of those little micro bunches is fully coherent, spatially and temporally coherent, but not coherent with their 100 little neighbors who are also fully spatially coherent amongst themselves. Okay.
So does that matter? Like if we need coherence, does it matter that one microbunch isn't in phase with the other one, or does it just matter that a given microbunch is coherent?
Well, one of the things that affects is the power that's radiated, because you've spread out your phase effects, your coherent phase effects amongst 100 different bunches. So that means that there's a lot less electrons than there could have been radiating in phase. If you were to make let's say a hologram or some other coherent thing. If you were going to do some scattering, small angle scattering, say, and you wanted to have as small an angle as possible, this probably wouldn't hurt you too much because they'd all have the same small angle. They'd have a little frequency difference. So your frequency width of what you were starting with for the income, for the scattering process would be a little wider. Okay. Yeah. So, yeah. Okay. So let me see what happens. Hopefully this is not a disaster. So far it's a disaster. Oh. Okay. Boop, boop, boop. Yeah. Can you guys see this now while I'm in slide sorter? Does it show? Oh, okay, great. Whoops, where's the diagram I'm looking for? So you can see this? Yeah, so here's the bunch of electrons that are coming through the FEL, and this is maybe halfway through or something like that. And in different regions of the electron bunch, there are separate little spatially and temporally coherent waves of electrons which cover pretty much left to right, okay, with some well-defined frequency, okay? And all the electrons associated with this wave are radiating in phase and giving us lots of power, okay? But their wavelength could be slightly different because, for instance, if the spectral width that the FEL will support is 500, that means there could be a bunch of different wavelengths in here, all fitting within a 1 part in 500. Okay, so not a big spread in wavelengths, but there could be some spread. Okay, and there'll be a whole bunch of them, and these are each giving an n squared effect. But if there's 300 of these, let's say, and you had 3/10⁸ electrons in the total electron bunch coming through, and you had 300 of these different things that fit within the bandwidth, that means in each one there'd be 3/10⁸ over 300, so there'd be a million electrons participating on average in these different bunches. And so when you calculate the electric field gain, n squared, where that's the number of electrons, you're gaining only 10⁶. It's still a lot. You went from watts to megawatts, but they're each giving you a megawatt. What happened to my mouse? They're each giving you a megawatt, but there's several hundred of them. So there's several hundred megawatts. So you didn't lose completely. You lost some n squared effect, but you didn't lose all n squared effect. Whoa, 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 whoa. Okay, so I wonder if I could just, here's a good shot. We're jumping ahead of ourselves, but you can see here, where is, well, anyway, I really screwed it up. Let me just fix that real quick. You can see here that this is these are bunch of, this is pulse after pulse after pulse. So this is, it says 20 consecutive shots, pulses coming through at some decent repetition rate. And this is the photon energy. So this is the spectrum. And you can see it's a bunch of little spikes. So it's roughly radiating at 8.3 kilovolts, but there's a lot of spikes in there. And each of these spikes is associated with one of these little microbunches. So the picture coming clearer? Okay, now for another, now we ask for another miracle. What is going on here? Okay, so this is the slide we were at before, and it was just mainly to get the idea across of the scale, the wave, this radiation, this micro bunching is actually on a wavelength scale, and there's going to be a lot of these bunches. There could be as many as 300 or 500 at SLAC, for instance. By the way, this is a good time just to catch something that happens to be in this slide, although this is our energy equation, the rate of change of energy for the electrons, and there has to be some transfer of energy from the electrons into the photons for the photons to be radiating with such power. So this is, we're going to go through equations in a moment, but I follow the literature as it's used by the FEL accelerator people. And what we're going to talk about in a moment is the change in gamma, gamma being the electron energy. This has to go down. The electrons have to lose energy in order to put more power into the X-rays. But they're going to describe it, you'll see in a moment, in terms of what looks like an angle, but it's not an angle. It's a phase difference between the electron position in the undulator, Ku times Z. You know, Z is the distance moving through the undulator, and the propagation of the wave. And they're basically propagating together, and this is basically a measure of where you are in this field. So this would be like theta, would be along here. And it's a matter of where is the electron in this process. This is what they're going to call theta. So when you see it, it's not an angle, it's a phase between the electron positions and the crest of the wave. Okay, this is just a comment on phase space. It's a phrase I've probably already been using with you, but phase space refers to a multidimensional space in which the spatial and velocity coordinates of particles are described, and there'll be how many particles are there in different areas of configuration space and velocity space. So this could be just a 2D space for a one-dimensional modeling. In other words, one coordinate would be, let's say vertical would be position, and horizontal would be velocity, and you would be plotting all the different where are the electrons as a function of position and velocity. Okay, so that we call that phase space. And so the plasma people will know about this. For instance, the Vlasov equation describes the variation in phase space of where the electrons are in position and velocity. Okay, in some cases, rather than position and velocity, you'll have position and momentum. All the relativistic work will be that way, position and momentum. And sometimes rather than velocity or even momentum, there'll be energy. And in fact, I'm going to show you a few in a moment. So here is a simulation. I just wanted to expose you to these simulations. This is the way the accelerator people do these numerical simulations. So this is 3 different time steps. One is early on in the undulator where the electron motion, just in one period of the undulator, the electrons go up and come down and go back again. Okay, so it's just a sinusoidal motion, nothing special happening. Well down the undulator, the micro bunching has started to occur. In fact, if you go back here, you can see that the electron distribution or the electron density is pretty much constant throughout the entire period of the undulator. But here, where the bunching has started, this sharp electron phase starts to appear. So there's a hell of a lot of electrons. Just add them up vertically in this at this axial position, and not so much at the others. And that's that would be around saturation, where you've got the maximum number of electrons in a peak. And then if you go too far, we won't spend any time on this, but if you go too far, if you make your undulator too far, this beautiful, nice wave will be destroyed, okay? And so, and by the way, so one of the reasons to show you was this is written in terms of eta, where eta is a non-dimensional energy, gamma, for the electron. So if the electrons start with some incoming gamma 0 and they gain or lose energy, gamma will change. So this non-dimensional measure of the beam energy is eta. It's what the accelerator people use. It has some normalization here, but this is basically energy of the electrons, and this theta is the position within one period along the undulator period. And it's just a great place for me to bring it up. This is what they would call a phase space diagram, and how the phase space evolves in time. And conveniently for us, this is a normalized energy, and this is a position in the z direction. It's a phase between the electrons and the wave. Where are they in the wave? Another of the same. Saldin, by the way. So what we were hoping at a certain point for a Nobel Prize for John Mady and Claudio Pellegrini and Saldin. And I'm not sure if, we just don't know if it's ever going to happen, but Saldin is a Russian, okay? And they have a book. And here's the same sort of diagrams. Again, phase space diagrams. Okay, where are we? So now we want to start, we have some physical sense of why there's going to be an exponential process of growth, but now we want to find out, want to go through some mathematics of that. So what I decided to do is show you some slides for what the process is. And for those, for instance, who, if any of you are going into FEL accelerator physics, you should read the chapter and go through these mathematics that we're going to show in the next few slides. But for the rest of us, we just want to understand what's the process, what equations are they using, and how do they lead to this exponential process. So here's a diagram, looks awfully familiar to us from our undulators, okay? Here are equations of motion. This is the equivalent of F equals ma relativistically. This is the so-called momentum equation in fluid mechanics, okay? So it's the rate of change of momentum depends on the Lorentz force. So, and there's an energy equation. The rate of change of energy is V dot F. That sounds very familiar to us, where V dot F becomes this. It's a V and an E. The magnetic field drops out. It's not because it's weak, it's actually quite strong, but V dot V cross B. V cross B is orthogonal to V, so V dot that, it drops out. It's vector identity, this term with a V dot in front of it, identically zero. So this is the rate of equation of energy. Energy is only changed in a magnetic field if there's an electric field, but the magnetic field has nothing to do with the rate of change, with the change of energy. And we'll see in a moment, there's some mathematics I'll show you that this term comes out in the following way. We'll understand it. So we have two equations for the motion, equations of motion, and we have a third one, which is the wave equation for this growing wave. We have this one-dimensional wave, and it's growing in amplitude. And we're going to show in a moment that the rate of change of electric field with position z looks like this, and it depends on that same angle theta that I used the word angle by mistake, that same phase for where the electrons are within the wave, okay? Okay, so there we're going to have three equations, vector equations. We're going to find, and we're going to have three unknowns, and we're going to combine these, okay? And that's what I hope to do in the following slides. So here's our two equations of motion. And in this slide, we're just combining the two. We're leaving the one-dimensional wave equation for the next slide. But these two waves, using knowledge that we have about what is the velocity and how does it depend on k, are combined here. So I'm not expecting you to follow this exactly. I just want you to see that we're using the two equations of motion and we're combining them and using our knowledge of what we learned before about the velocity of oscillation in a magnetic field. And these terms appear. And for instance, for the velocity of the electron, in the magnet period, it depended on a cosine or a sine. It depended on how you drew what was the phase, okay? So this has to do with the electron position as a function of z in the undulator. The other one has to do with the wave propagation. And these two terms get combined. So all of this stuff out in front, these have to do with the parameters that we derived before, okay? But these two terms multiplying, okay, can be expressed instead in the following way, okay? And one of these terms is a very slow varying thing because the wave and the electrons are moving together. And the other one has a very high frequency, the fast part. And if you're looking to exchange energy, this one is exchanging it back and forth so quickly, it doesn't play a role and we wind up dropping it. And, convincing yourself that that's true, you have to go through that math in the chapter and even some in the appendices. It's this one that matters. And again, this theta is really just a measure of phase between the movement of the electron and the wavefront crests, okay? So the rate of change of energy depends on this. And as you know, mathematicians will want to, I was trying to get rid of something that was in my way. So to solve these equations, the accelerator community introduces a relative energy change, gamma minus gamma zero over gamma zero. So that's where this eta is the relative energy shift, okay? And theta is introduced from these two terms. And there's a fast frequency and a slow frequency, okay? They both have this undulator frequency of how fast the electron goes through sets a frequency, but one has an eta. And eta is a relatively small quantity, okay? And this is going to be the slower part, okay? And so, for instance, d eta dt becomes something like this. These two equations wind up leading to these two equations. And this is for slowly varying electron position and energy. So this is the phase position of an electron within the wave, and it depends on eta. So the position theta depends on the energy change, and the rate of energy change depends on theta. So these go with that diagrams I was showing you, but these two equations are now combined in terms of new parameters, eta and theta, okay? And the third equation is the one-dimensional wave equation. And again, this is in the book, and you're writing a wave equation like this, and you're assuming that your electric field has the usual e to the minus omega t minus k dot r, but the amplitude now is shown with a little tilde on the top to indicate that this is a complex quantity. This allows for either damping or growth, and it'll be wave growth that we're interested in. And you not only have to go to the chapter, but you have to go to an appendix to work through all of this, the algebra that's here, the calculus. But basically what you find is that the electric field amplitude varies in z, as shown here. So it also depends on this theta. Okay, so that's our third equation. So these become the momentum, energy, and one-dimensional wave equation. These are the three so-called undulator equations. So you may not have derived them, but you have been exposed to them, and they're just interdependent. Theta depends on eta, eta depends on theta, the electric field depends on theta, and these are nonlinear terms. This has the electric field is one variable, and theta is another. So this is a product term. Okay, so this is nonlinear. This is not, but this is nonlinear, and this is also needs to be dealt with. So in a moment, we're going to, the next slide just shows these same three equations linearized. Okay, these are the three equations after linearization. So for instance, this term, this E sub x, was here. Cosine of a small angle, this becomes unity. This perturbation, small angle, that becomes this. Okay, so do we have enough to do? Yeah, we have 3 or 4 minutes. These three equations can be combined into a single third order equation, which looks like this. So we have Claudio Pellegrini to thank for this, okay, and for what follows from it. So it's saying that the electric field satisfies a third order equation with some gamma, and this is gamma. They call it the gain parameter. And it just collected all of these different natural units here, including the K of the magnetic field. The caret is a small issue I don't want to describe to you right now, but we could just imagine that it's K squared. Okay, and so how do you solve this equation? You assume that electric field, this electric field with the tilde on top, has a form of some magnitude of electric field, let's say starting someplace, and in e to the mu z, where mu we don't know, okay? But from the previous equation, here, we can find that mu cubed is I gamma cubed. So the so-called dispersion relationship just came from that previous equation with this substitution. Substitute this in, this is what you get, okay? So there are 3 solutions for mu, and this is the 3 solutions, mu1, mu2, and mu3. Mu1 is a imaginary term. The electric field is just oscillating. It's not gaining, the amplitude is not changing, it's just oscillating. U2 and U3 both have an oscillatory component. That's what the I is about. But one has a minus sign for the other term, and one has a plus sign. And if you plug them in here, one of them means it's a decaying, oscillating but decaying wave. The other one is oscillating but amplifying. And so it says here, the third wave corresponds to an exponentially growing amplitude. So you plug this one in here, and your third order equation gives you this solution, okay? So the electric field starts with some amplitude, it oscillates in Z, okay? And it grows exponentially. This is the one we want for the FEL. And the power, of course, goes as the electric field squared. So it's going to be this thing, actually modulus squared, right? So these things cancel out, E0 squared, and here you would have Z squared over LG. Where LG depends on the parameters on the previous page. It depends on lambda U, the undulated period, and this FEL. And remember, so this is about this is like 20, something like that, okay? It's just a constant. And this is a number like 1 over several hundred. So the gain length, which is the gain length is what is the distance for the electric field to gain by a factor of E. That is a gain length, okay? And it shows up to be a few hundred cycles. So all of this, the mathematics of it is, one of the important things is what's captured in rho FEL, which is not shown here. It's on the next slide, okay? So the gain length is shown here, and rho FEL that it depends on is this factor that includes all kinds of things in it, okay? And this, as I said, will be a number something like 300, or 1 over 300 or 500. And what Pellegrini showed was that in this FEL, this SASE process, not only does the gain length depend on rho FEL, but the bandwidth depends on FEL, and the saturated power, the radiated power, depends also on rho FEL multiplied by the total energy in the beam. This is the energy of each electron, and this is how many electrons there are. Okay. I think I'll save this for next time. Let's see what else is there. So basically we combined 3 equations, 2 for the particles, momentum and energy, and a wave equation, but a wave equation going only in one direction. It's not radiating much to the sides. And in combining them, we not surprisingly got a cubic equation. And that cubic equation with all of these factors in it looks like this. And then you can solve this by assuming in a solution where E sub x, had the wrong button, where E sub x has this exponential factor, and you've assumed nothing here by mu. If you plug this in, you get this, and you find there is cubic equations, got 3 solutions, and one of them is an amplifying solution, okay? And it's amplifying with a gain length that's shown here. So that is a good place for us to stop. We'll come back to it next time. Okay, so I would suggest that you read some parts of chapter 6. You know, you don't have to get lost in the math, but at least have some awareness that it's there. And I hope this outline of where which 3 equations and how to usual process for combining equation, just difficult to follow because you know, the normalization into an eta and a theta, etc. So I think I'll end there, but certainly open to any questions or comments. No? Okay. So see you Thursday.